Hello everyone, we are excited to present our project Microcontroller-Based Washing Machine Simulation using PicsimLab. It was developed as a part of our Embedded Systems internship. Firstly, we would like to thank EMERTXE for this wonderful opportunity. This hands-on project allowed us to apply our knowledge in practical and meaningful way. Our team, Rama, Kintan, Karthik, and myself, Akshaya, worked together for this project. Coming to the introduction, in today's world, washing machines have become essential in reducing manual effort and improving household efficiency. With the integration of embedded systems and microcontrollers, the traditional machines have evolved into smart and automated appliances. The modern washing machines are now intelligent, user friendly, and energy efficient. This project mainly focuses on designing a smart washing machine system using the PIC16 F877A microcontroller with an emphasis on reliability, automation, and user adaptability. And our main goal was to simulate a real world washing functions in a compact and cost effective prototype. And now coming to what is embedded systems and applications. An embedded system is a combination of hardware and software designed to perform a specific task. It uses a microcontroller or a microprocessor and is usually a part of a larger system. It works in real time, often with constraints on power, memory, and performance. And their key applications include automobiles such as airbags and engine control, consumer electronics like washing machines and smart TVs, medical devices including pacemakers and monitors, IoT applications such as smart homes and wearables, and also used in industrial applications like robotics and automation controllers. Embedded systems can be classified into several types. Real time embedded systems. These systems respond within a strict time frame, for example, airbag systems and industrial robots. Standalone embedded systems. These operate independently without any host system. Example, washing machines and calculators. Networked embedded systems. These are connected to a network to access or share resources. For example, IoT devices. Mobile embedded systems. These are mainly designed to be portable and power efficient. For example, smartphones and smartwatches. Small, medium, and large scale systems are mainly classified based on processing power and complexity. Example for a small scale system is a digital watch, for medium scale security systems, and for large scale systems aerospace or smart car systems. C and embedded C. C is a general purpose programming language used for developing software across platforms. Embedded C, on the other hand, is used to program microcontrollers in embedded systems. The key differences are C runs with an operating system and uses standard libraries. Embedded C runs directly on hardware and accesses the registers directly. While C is commonly used in software applications, embedded C plays a vital role in developing IoT devices, automotive controls, and home appliances. The further slides are presented by my teammate.
Thank you, Akshaya. I am Karthik. I am going to explain about block diagram of embedded systems. It contains central processing unit, read-only memory, random access memory, input devices, output devices, communication interfaces, and application-specific circuitry. Memories and its types. Embedded systems use memory to store code and temporary data during operation. Memory is chosen based on speed, size, power and cost. ROM, read-only memory. It stores permanent code and it's non-volatile. Types of ROM: mask ROM, PROM, EEPROM, EEPROM, flash. RAM, random access memory. It stores temporary data during execution. and it's volatile. Types of RAM: SRAM, fast, costly, used for cache; DRAM, slower, cheaper, used for main memory; cache, high speed memory for storing frequently used data sites between CPU and RAM; registers, small, fast memory inside the CPU, holds immediate values for operations; MPLAB IDE, it is used for our project. Developed by Microchip for 8-bit PIC microcontrollers. Works seamlessly with MPLAB XIDE. Supports PIC10, PIC12, PIC16 and PIC18 families. Offers high efficiency code generation for optimized performance. Includes built-in libraries for peripherals like ADC, PWM, UART and timers. It allows bit level and register level control of microcontroller features. It supports interrupt service routines ISRS and embedded C syntax used in projects for writing firmware like sensor reading, display control, motor drivers. Exec compiler. It is a C compiler developed by Microchip for 8-bit PIC microcontrollers. Works seamlessly with MPLAB XIDE. It supports PIC10, PIC12, PIC16 and PIC18 families. It offers high efficiency code generation for optimized performance. It includes built-in libraries for peripherals like ADC, PWM, UART and timers. It allows bit level and register level control of microcontroller features. It supports interrupt service routines, ISRS and embedded C syntax. It is used in projects for writing firmware like sensor reading, display control, motor drivers. PicsimLab. PicsimLab is a graphical simulator for PIC microcontroller-based circuits. It is useful for testing and debugging embedded C code without physical hardware. It simulates hardware components like LEDs, switches, LCDs, buzzers, relays. It supports .hex files generated from MPLAB XE8 compilation. Integrates with PicSim backend and supports multiple PIC devices, example PIC164877A. It allows real-time simulation of microcontroller input and output and peripherals. Ideal for learning, prototyping and debugging embedded systems projects. It is lightweight, open source and works on Linux and Windows platforms also. Introduction to our project. This project is a microcontroller-based automatic washing machine. It is designed using PIC164877A microcontroller programmed in embedded C using MPLAB XE8. Mimics real washing machine functionalities, wash, rinse, spin, and dry cycles. Integrates user input, output display like CLCD, indicators, LEDs, buzzer, fan for a complete system. It demonstrates practical use of timers, interrupts, and peripheral interfacing in embedded systems. It provides a user-friendly interface for mode selection and cycle control. It creates a cost-effective prototype for educational and practical demonstration. PIC16F877 microcontroller. It is a 8-bit microcontroller from Microchip's PIC16 family. It is based on RISC architecture with 35 simple instructions. Runs at speed up to 20 MHz with high performance CMOS technology. Memory 8K flash, 368-byte RAM and 256 bytes EEPROM. .33 I/O pins with multiple functions. It's a built-in peripherals like 3 timers, 10-bit ADC, USART serial communication, SPI and 12C support, PWM modules, watchdog timer. It's a wide operating voltage 2 volts to 5.5 volts suitable for embedded projects. Frequently used in home automation, robotics, data logging and control systems. Digital keypad. Matrix type keypad. Example 4 into 3. Used for user input in embedded systems. It works on row column scanning using GPIO pins. Requires software debouncing to avoid false key detection. Commonly used in menu navigation, automation and control systems. In this project, use it to select wash modes, set timers and start or stop cycles. Interfaced with PIC16F877A and programmed using MPLAB XC8. It is integrated with CLCD to show user-selected options. It enhanced user interaction and made the system menu-driven and user-friendly. Timers. Timers in microcontrollers count clock pulses or actional events and can operate in timer, internal clock, or counter actional event mode. They are configurable as 8-bit or 16-bit and are commonly used for generating delays, periodic interrupts, PWM signals, and event counting. PIC16F877A includes timer 0, timer 1, and timer 2, which are frequently used for various timing operations. In this project, timers generate 1 second delay for the countdown and control operation durations such as 10 seconds for wash and 8 seconds for rinse. Timers also manage real-time sequencing of washing machine functions using interrupt-based delays. My friend Kintan will continue.
Thank you, Karthik. I am Kintan Varma. I will continue from here. A CLCD character LCD like the 16 into 4 used in this project displays text, numbers, and symbols across 4 lines with 16 characters each. It operates in 4-bit or 8-bit mode. 4-bit mode is used here to save GPIO pins using control lines RS, RW, EN, and data lines D4 to D7. The display is driven by an HD44780 compatible controller, commonly used for system status, menus, sensor data, and user messages. In this project, the LCD shows the selected wash mode, countdown timer, current operation, and user prompts. It is interfaced with the PIC16 F877A in MPLAB XC8, improving usability and reducing the need for additional indicators. Tactile switch. A tactile switch is a mandatory push button that provides tactile feedback and makes contact only when pressed. It is typically an SPST normal open switch, commonly used for functions like start, stop, mode select, and reset. In microcontroller systems, it connects to GPIO pins with pull-up or pull-down resistors and requires debouncing to prevent false triggers. In this project, tactile switches are used to control and trigger wash cycle stages on the PIC16 F877A. They are detected using polling or interrupts in MPLAB XC8, offering a simple, cost-effective, and reliable input method. ISR. ISR is a special function that executes automatically in a response to interrupt signal. Temporarily pauses the main program, handles the event, then returns to normal execution. Commonly triggered by timers, external pins, ADSC completion, UART, etc. Must be written to execute quickly and efficiently to avoid delays. In projects like washing machine, ISRs are used for timing counting, button presses, or real-time event handling. LED. LEDs are semiconductor devices that emit light when powered and are widely used as status indicators in embedded systems. They require current limiting resistors 220 ohms to 1 kilo ohms and are controlled via GPIO pins using high or low signals. In this project, LEDs indicate wash, rinse, and spin states to show the current operation phase. Interfaced with the PIC16 F877A and controlled using MPLAB XC8 for real-time visual feedback. They offer a simple, low power and effective way to enhance system visibility alongside the LCD. Buzzer. A buzzer is an audio signaling device that emits a beep or tone when powered, using, used for alerts, status notification, and end of cycle indication. Operated through a microcontroller GPIO pin using high or low signals or PWM. In this project, it signals cycle completion or error states for user awareness. It provides an audible, low power, and cost effective feedback mechanism. Fan. A fan is an electromechanical device used for air circulation or cooling, controlled via transistor or relay interfaced with a microcontroller out pin. In this project, the fan operates during the spin dry phase to aid drying, driven using GPIO control in MPLab X8, allowing time-based activation. It enhances functionality by supporting effective drying in the wash cycle. Thank you. From now onwards, my friend Rama will continue.
I am Rama. I am going to explain the project which I have completed in 1 month internship of embedded systems in EMERTXE. Now we are going to observe the coding part of washing machine in MPLab. Now working the washing machine project, you have to create source files. Main.c. Main.c is a main file in which the more source files and the modules is there to execute the program. And clcd.c. clcd.c is used to control the display of washing machine and microcontroller. Now, digital keypad. Digital keypad is used to control the input switches like RB0, RB1, RB2, RB3, etc. ISA.c. It is an interrupt file, and project function.c is a file which is very important to observe programs, water level, and etc. And in this file there are different modules to execute, and timers.c is used to handle the delays in washing machine stages. We have to create header files, where the header files is used to define the values, registers, and switches. Like for cncd.h, we have to define the DDR, data direction register. Like we are assigning registers trends D, try register port D. Like that we have to assign different values. We are giving values for blocks, and we are giving values and then registers. For CLCD, we have created header file and digital keypad.h. This is for digital keypad. This is for whole project, washing machine project, and then this is for project function.c, and then timers.h is for timers. After that, we have to execute the program by build project. And it shows build successfully. If it shows build successful, then you have successfully completed the execution through code. Now we have to observe real-time working of washing machine in PicsimLab. If you get any errors, then observe in output box. Now we are going to observe the real world application working in PicsimLab. Now it is an interface of PicsimLab. To observe here, you can select microcontroller. There are different types of microcontrollers available. We are using PIC16F877A. You can select clock frequency here. I am taking 20 MHz and I am using LCD display is 16 into 4. If you want 16 into 2, then you can. But I am using 16 into 4 for better experience. And then you have to select load hex. Go through hex file and open it. Then it automatically run. It shows press switch 5 to power on washing machine. I am going to powering on my washing machine. Yes, it is working. Now it shows washing programs. There are different types of washing programs like daily, heavy, delicate, whites, stain wash, eco cloths, linens, bed sheets, rinse plus dry only, wash only, egg wash only. Now I am going to select daily wash. If you want to select particular program, then you have to long press on switch 4. Now it shows the water level. In water level, there is 5 different types: auto, low, medium, high, and max. I am going to select high. So I have to long press on switch 4. Now it shows press switch. If I switch, click on switch 5, then it will start. If I click on switch 6, then it will stop. I am going to start washing. It shows the time and the machine is working and the fan is running. See there. Now the time is running. If the time is stopped, then it will show the program is completed. Remove clothes. If I want to pause, then I have to click on switch 6. Now it is paused. Now I am going to start again. After that time ends, then it shows the program is completed and remove clothes. If I want to open door, it shows the door is open. Please close the door. It shows program completed and remove clothes. The execution is completed. Now I am going to complete this project and I will give conclusion. Conclusion. Successfully designed and implemented a microcontroller-based washing machine prototype using PIC16F877A. Achieved automatic control of washing, rinse, spin and dry cycles with real-time feedback. Integrated various components like keypad, 16x4 CLCD, LEDs, buzzers and fan effective. Demonstrated the use of timers, interrupts and peripheral interfaces in embedded system design. Provides a cost-effective, scalable and educational solution for real-world embedded applications. Thank you.